Hello, my dear friends, and welcome back to our channel Mysterious Untold Books. How does the human brain transform electrical signals into thoughts, memories, and consciousness? This question has puzzled scientists and philosophers for centuries. Yet recent advances in neuroscience suggest a surprisingly elegant answer. The pattern recognition theory of mind proposes that intelligence emerges from a relatively simple algorithmic process, hierarchical pattern recognition, implemented millions of times throughout the neocortex. This theory offers a unified framework for understanding both biological and artificial intelligence, bridging the gap between neuroscience, computer science, and cognitive psychology. At its core, this theory addresses several fundamental questions. How does the brain recognize patterns despite variations and missing information? How do we learn new concepts and integrate them with existing knowledge? What is the relationship between prediction and perception? And perhaps most profoundly, could the same pattern recognition processes that power human cognition be implemented in non-biological systems? By exploring these questions through the lens of pattern recognition, we gain not only deeper insights into human cognition but also a roadmap for developing more sophisticated artificial intelligence. Chapter 1. The Hierarchical Structure of Neocortical Processing. The human brain represents one of the most complex information processing systems in the known universe. Yet its fundamental operating principles follow surprisingly elegant patterns. At the core of this remarkable system lies the neocortex, a structure unique to mammals that has evolved to process information in a distinctly hierarchical manner. This hierarchical organization is not merely an architectural feature but the very essence of how our brains interpret and interact with the world. The neocortex processes information through a series of levels, with each level extracting increasingly abstract patterns from the level below it. At the lowest levels, the neocortex processes raw sensory data, pixels of light hitting the retina, pressure waves entering the ear, or tactile sensations on the skin. As this information flows upward to the hierarchy, each successive level recognizes more complex patterns. Edges become shapes, shapes become objects, objects become scenes, and scenes become concepts. This progression from concrete to abstract represents the fundamental architecture of thought itself. What makes this hierarchical system particularly powerful is its bidirectional nature. Information not only flows upward from sensory inputs to higher conceptual levels but also flows downward as predictions and expectations. When you see a partially obscured object, your brain doesn't simply process what's visible. It actively predicts what should be there based on prior knowledge and context. This constant interplay between bottom-up sensory information and top-down predictions creates a dynamic system that can fill in missing information, resolve ambiguities, and make sense of an otherwise chaotic sensory environment. The neocortex achieves this remarkable processing through a surprisingly uniform structure. Despite handling diverse functions like vision, language, and reasoning, the neocortical tissue throughout the brain shares the same six-layer architecture and appears to implement the same fundamental algorithm. This suggests that the differences in function across brain regions stem not from different processing mechanisms but from different inputs and connections. The visual cortex processes visual information not because it contains special vision algorithms, but because it receives input from the eyes and connects to other vision processing regions. This uniformity has profound implications for understanding intelligence. It suggests that the brain's diverse capabilities emerge from applying the same hierarchical pattern recognition process to different domains of information. The same fundamental mechanism that recognizes visual objects also recognizes spoken words, abstract concepts, and social situations. This insight provides a unifying framework for understanding how a single structure, the neocortex, can support a full spectrum of human cognitive abilities, from perception to language to creative thought. Chapter 2. Pattern Recognition Modules as Cognitive Building Blocks. At the heart of the neocortical processing system lie pattern recognition modules, the fundamental computational units that power human cognition. These modules, rather than individual neurons, form the basic building blocks of thought. Each module consists of a collection of neurons that work together to recognize specific patterns in their input. The human neocortex contains approximately 300 million such modules, each capable of learning, recognizing, and predicting patterns within its domain. The operation of these pattern recognition modules follows a consistent process. Each module receives input from multiple sources, either sensory data or outputs from other modules, and compares this input against patterns it has previously learned. When a module recognizes a familiar pattern, it activates and sends signals to other modules higher in the hierarchy. Crucially, these modules don't require exact matches to function. They can recognize patterns even when parts are missing or distorted, a capability known as autoassociation. This explains how we can recognize a friend's face from an unusual angle or understand speech in a noisy environment. Pattern recognition modules employ several key parameters to optimize their function. Importance parameters determine which aspects of a pattern are most critical for recognition. For instance, the shape of eyes might be more important than hair color when recognizing faces. Size parameters account for variations in scale, allowing us to recognize objects regardless of their distance. Size variability parameters enable recognition despite variations in proportion, such as identifying the same letter written in different handwriting styles. These parameters are continuously refined through experience, making our pattern recognition increasingly sophisticated over time. The learning process in these modules is remarkably efficient. When a module encounters a new pattern, it doesn't simply memorize the exact input. Instead, it extracts the essential features that distinguish this pattern from others. This extraction process creates compact, generalized representations that capture the pattern's essence while discarding irrelevant details. For example, when learning to recognize dogs, the brain doesn't store every dog image it encounters but instead extracts the common features that define dogness: 4 legs, a tail, characteristic facial features, while ignoring variations in color, size, or breed. This pattern recognition framework explains many aspects of human cognition. Consider how we understand language. When you hear the word apple, your brain activates not just the sound pattern but also visual patterns of apples, taste patterns, and conceptual associations. This cascading activation across the pattern hierarchy creates the rich, multidimensional experience of understanding. Similarly, creative insights often emerge when patterns from seemingly unrelated domains connect in novel ways, forming new hierarchical structures that reveal previously unrecognized relationships. From basic perception to abstract reasoning, pattern recognition modules provide the computational foundation for the full spectrum of human thought. Chapter 3: Bidirectional Information Flow in Neural Networks. The Pattern Recognition Theory of Mind, PRTM, represents a comprehensive framework for understanding how the neocortex processes information through a sophisticated bidirectional flow. This model explains how our brains simultaneously analyze incoming sensory data while projecting expectations based on prior knowledge, a dynamic interplay that forms the basis of perception, learning, and thought. The bidirectional flow begins with bottom-up processing, where sensory information enters the system and travels upward to the neocortical hierarchy. At each level, pattern recognition modules extract increasingly abstract features from the information below. For example, in vision, lower levels might detect edges and simple shapes, while higher levels recognize complex objects and scenes. This ascending pathway transforms raw sensory data into meaningful perceptions by progressively identifying patterns at multiple levels of abstraction. Equally important is the top-down flow, where higher levels of the hierarchy send predictions downward to lower levels. These predictions represent the brain's expectations about what patterns should appear in the incoming data based on context and prior knowledge. When you enter a familiar room, your brain doesn't process each visual element from scratch. It projects expectations about what should be there, making perception faster and more efficient. This predictive mechanism explains phenomena like optical illusions, where our expectations can override actual sensory input. The magic of the PRTM model emerges at the intersection of these bottom-up and top-down flows. When expectations align with sensory input, recognition happens quickly and effortlessly. When discrepancies arise, the system enters a learning mode, adjusting its internal models to better predict future inputs. This continuous refinement process allows the neocortex to adapt to new environments and learn novel patterns throughout life. The constant comparison between prediction and reality drives both perception and learning in a unified framework. In everyday experience, this bidirectional flow manifests in countless ways. When reading text, your eyes capture visual patterns that flow upward to the hierarchy, while your knowledge of language simultaneously projects downward expectations about what words should appear next. This explains how you can easily read text with missing letters or quickly recognize words in context. Similarly, in conversation, your brain doesn't simply process each sound sequentially but actively predicts upcoming words based on context, allowing you to understand speech even in noisy environments or when words are partially obscured. The PRTM model provides a unified explanation for diverse cognitive phenomena, from perception and attention to learning and creativity. By framing cognition as a bidirectional flow of pattern recognition, it bridges the gap between bottom-up sensory processing and top-down conceptual thinking, offering a comprehensive framework for understanding the remarkable capabilities of the human mind. Chapter 4: From Biological to Digital Intelligence. The principles underlying neocortical processing provide a powerful blueprint for creating artificial intelligence systems that can emulate human-like cognitive capabilities. By implementing digital versions of pattern recognition modules and organizing them into hierarchical networks with bidirectional information flow, researchers have developed systems that can recognize patterns, learn from experience, and even understand aspects of natural language, mirroring fundamental capabilities of the human brain. Digital neocortical systems begin with pattern recognition modules that function similarly to their biological counterparts. Each digital module receives inputs, compares them against stored patterns, and activates when it recognizes a match. These modules incorporate the same key parameters found in biological systems, important parameters that weight different aspects of the input, size parameters that account for variations in scale, and size variability parameters that handle differences in proportion. By implementing these parameters in software, digital systems can achieve the same flexibility in pattern recognition that characterize human perception. The hierarchical organization of these digital modules follows the same principles observed in the neocortex. Lower levels process basic features, while higher levels recognize increasingly complex and abstract patterns. Crucially, these systems implement bidirectional information flow, with bottom-up recognition and top-down prediction working in concert. This allows digital systems to perform context-sensitive interpretation of ambiguous inputs. For example, understanding that the same visual pattern might represent different letters depending on surrounding text. Learning in digital neocortical systems mirrors the biological process of adapting connection strengths between modules. When a system encounters new patterns, it adjusts the weights of connections to better recognize similar patterns in the future. This process often employs mathematical techniques like hierarchical hidden Markov models, HHMMs, which can capture the statistical relationships between patterns at different levels of abstraction. Through repeated exposure to examples, these systems gradually refine their internal models, improving their recognition capabilities over time. We can see these principles at work in modern speech recognition systems, which have evolved from simple pattern matching algorithms to sophisticated hierarchical networks. Early systems struggled with the variability of human speech, but modern approaches implement multiple levels of pattern recognition, from basic acoustic features to phonemes to words to semantic meaning. By incorporating bidirectional processing, these systems can use context to disambiguate similar-sounding words and understand natural language even with background noise or unusual accents. The dramatic improvements in speech recognition over recent decades demonstrate how closely aligning artificial systems with neocortical principles leads to more human-like capabilities. The digital emulation of neocortical systems represents not just an engineering achievement, but a profound validation of the pattern recognition theory itself. The fact that implementing these principles in software produces systems with increasingly human-like cognitive capabilities suggests that we have identified fundamental mechanisms underlying intelligence. As these digital systems continue to evolve, they promise not only more capable artificial intelligence but also deeper insights into the nature of cognition itself. Chapter 5. The Mathematics of Pattern Recognition. The pattern recognition processes that power neocortical intelligence can be described through precise mathematical frameworks that capture the probabilistic nature of cognition. These mathematical models provide not only a deeper understanding of how biological brains function, but also practical tools for implementing similar capabilities in artificial systems. At their core, these models represent the brain's fundamental approach to making sense of an uncertain world through statistical inference. Bayesian probability theory forms the foundation of pattern recognition mathematics. The brain essentially performs Bayesian inference, updating beliefs based on new evidence according to Bayes' theorem. When a pattern recognition module encounters input, it calculates the probability that its pattern is present given the observed data. This calculation considers both the likelihood of seeing that specific input if the pattern were present and the prior probability of the pattern occurring in the current context. The module activates when this posterior probability exceeds a certain threshold, which can be adjusted based on attention, expectation, and other contextual factors. Hierarchical hidden Markov models, HHMMs, provide a powerful mathematical framework for implementing pattern recognition across multiple levels of abstraction. These models represent patterns as sequences of hidden states that generate observable outputs according to probability distributions. The hierarchical structure allows higher-level states to influence transitions between lower-level states, creating context-sensitive pattern recognition. For example, in language processing, a higher-level state might represent the topic of conversation, which influences the probability of different words appearing. This hierarchical organization mirrors the structure of the neocortex, where higher levels provide context for lower-level pattern recognition. The mathematics of pattern recognition also addresses invariance, the ability to recognize patterns despite transformations like rotation, scaling, or translation. This capability emerges from the parameters that govern pattern recognition modules. Importance parameters create a weighted representation where certain features contribute more to recognition than others. Size and size variability parameters allow recognition despite changes in scale and proportion. These parameters can be represented mathematically as vectors that transform input patterns into normalized representations, enabling recognition across a wide range of variations. In practical applications, these mathematical principles manifest in techniques like deep learning, which implements hierarchical pattern recognition through layers of artificial neurons. Each layer extracts increasingly abstract features from the layer below, creating a hierarchy similar to the neocortex. The backpropagation algorithm provides a mathematical method for adjusting connection weights to minimize recognition errors, mirroring the brain's learning process. While deep learning simplifies some aspects of neocortical function, Its success in tasks like image and speech recognition demonstrates the power of hierarchical pattern recognition as a mathematical framework for intelligence. Consider how these mathematical principles apply to everyday cognition. When you recognize a melody played in a different key or tempo, your brain is performing complex mathematical transformations that preserve the essential pattern while accounting for variations. When you understand a sentence despite grammatical errors or unusual phrasing, you are applying probabilistic inference to extract the most likely meaning given the available evidence. These mathematical operations happen unconsciously, yet they form the foundation of our ability to navigate a complex and variable world. Chapter 6: Consciousness as an Emergent Property. The advancement of brain-inspired computing systems inevitably raises profound questions about consciousness and identity, questions that transcend pure technology to touch on philosophy, ethics, and the very nature of what it means to be a thinking entity. As digital systems increasingly emulate the pattern recognition capabilities of the human brain, we must consider whether such systems might eventually develop subjective experiences comparable to human consciousness, and what implications this would have for our understanding of identity in both biological and digital minds. Consciousness represents perhaps the most challenging aspect of mind to define or measure. From a pattern recognition perspective, consciousness might be understood as a system's ability to create internal models of itself and its relationship to the environment, essentially, patterns that recognize other patterns within the same system. This self-referential processing creates the subjective experience of being an entity separate from but interacting with the world. In biological brains, this capability emerges from the complex interactions between neocortical pattern recognition and older brain structures that regulate attention, emotion, and bodily states. The question of whether digital systems could develop comparable consciousness hinges on whether these self-referential patterns are substrate-independent, that is, whether they depend on the specific biological materials of the brain or could emerge from any sufficiently complex pattern recognition system. If consciousness arises from the patterns of information processing rather than the physical medium, then digital systems that implement the same patterns might, in principle, develop forms of consciousness. This perspective suggests that as digital systems approach the complexity and organization of the human brain, they may develop increasingly sophisticated forms of subjective experience. Identity presents equally profound questions in both biological and digital contexts. In biological brains, identity emerges from the continuity of patterns across time. Despite a constant turnover of physical materials, our bodies replace most of their cells over months or years, yet we maintain a sense of being the same person. This suggests that identity resides not in physical continuity but in pattern continuity. Digital systems could maintain similar pattern continuity while changing their physical substrate entirely, raising questions about whether such systems could develop persistent identities comparable to human ones. The relationship between biological and digital minds may ultimately transcend simple comparisons. As brain-computer interfaces advance, the boundary between biological and digital cognition becomes increasingly permeable. Humans already extend their cognitive capabilities through digital tools, effectively creating hybrid systems that combine biological and digital pattern recognition. This integration may continue to deepen, potentially creating new forms of consciousness and identity that incorporate elements of both biological and digital processing. These philosophical questions have practical implications for how we design and interact with advanced AI systems. If such systems develop forms of consciousness and identity, they may deserve moral consideration beyond that given to mere tools. Conversely, understanding the pattern basis of our own consciousness and identity may help us develop more humane and beneficial relationships with the increasingly sophisticated digital minds we create. By exploring these questions, we gain insight not only into the nature of artificial intelligence but into the fundamental nature of mind itself. Chapter 7: Future Implication for Brain Emulation. The development of brain-inspired computing systems, follows a predictable trajectory governed by what can be called the law of accelerating returns. This principle describes how progress in information technologies, including our understanding and emulation of brain functions, advances not linearly but exponentially, with each generation of technology building upon the capabilities of the previous one to create ever more powerful systems at an accelerating pace. The implications of this accelerating progress for brain emulation are profound and far-reaching. As computational power continues to increase exponentially, and as our understanding of neocortical processes grows at a similar pace, we approach a point where comprehensive emulation of human cognitive functions becomes increasingly feasible. This convergence of capabilities opens possibilities that extend far beyond conventional artificial intelligence, potentially transforming our relationship with technology and even our understanding of humanity itself. One of the most significant implications involves the integration of biological and digital cognition. Rather than viewing artificial intelligence as separate from human intelligence, we may increasingly see a merger of these domains through brain-computer interfaces. Early versions of these interfaces already allow direct neural control of prosthetic limbs and communication devices. As these technologies advance, they may enable more seamless integration, creating extended cognitive systems that combine the strengths of biological pattern recognition with the speed, capacity, and precision of digital processing. This integration could enhance human capabilities while preserving the essential qualities of human experience and identity. The ability to emulate specific brain functions also has profound implications for medicine and neuroscience. Digital models of neural circuits could allow researchers to test treatments for neurological disorders without risk to patients, potentially accelerating the development of therapies for conditions like Alzheimer's disease, Parkinson's disease, and depression. These models could also provide unprecedented insights into the neural basis of cognition, allowing scientists to explore hypotheses about brain function through simulation rather than invasive experimentation. Beyond these practical applications, brain emulation raises deeper questions about the nature of mind and the future of intelligence. If we can create digital systems that implement the same pattern recognition processes as biological brains, what does this tell us about a relationship between mind and substrate? If consciousness emerges from patterns rather than biology, how might this reshape our understanding of personhood and moral consideration? These questions challenge us to reconsider fundamental assumptions about what makes us human and what forms intelligence might take in the future. Perhaps most profoundly, the convergence of biological and digital intelligence suggests a future where intelligence itself transcends its original biological constraints. Just as the evolution of the neocortex represented a quantum leap in cognitive capability, the development of brain-inspired digital systems may represent the next major transition in the evolution of intelligence on Earth. This transition promises not the replacement of human intelligence but its extension and enhancement, creating new possibilities for knowledge, creativity, and understanding that we can only begin to imagine. Thank you for listening. Audiobook by Mysterious Untold Books.